Welcome. Today we are going to be evaluating an integral using spherical coordinates. You can tell it's spherical because all of this interesting spherical notation is being used. First of all, we need to get the conversion formulas stated. So x is going to be equal to rho sine phi cosine theta. Y is going to be equal to rho times sine phi sine theta, and z is going to be equal to rho cosine phi. Also, we're going to have the dv be equal to rho, that's a bad rho squared sine phi, and then that will be d rho d phi d theta, or whatever order we need to state those in. So let's get a description of the domain of integration here so that we know what bounds to use. Between the spheres rho equals 2 and rho equals 4, that means that we're looking at rho being, it's pretty explicitly stated, between 2 and 4. Above the cone, phi equals pi over 3. What that means is that phi, remember, it counts the angle from the positive z-axis tilting downwards. So by the time it gets to pi over 3, that means that it's gone through this much of an angle, okay? It's gone from up here to down there. So that's why this is called a cone, because at this point, that's where you've had this line that goes through an angle of pi over 3. So you're going to be integrating as phi goes from 0, that's on the positive z-axis, up until pi over 3. That's as it tilts downwards. Now we want this between the spheres and above the cone. There's no statement made about any restriction in rotation around the xy plane. So we're going to assume that theta spins around the whole thing, which means 0 to 2 pi. Okay, so now we're ready to set up the integral. X, y, z times rho squared sine phi. This is going to be the integrand. And x, y, z is going to be rho, but then also times rho squared. That'll be rho to the 5th. Now look at how many times the other things happen. We've got sine phi, and sine phi. That's going to be sine cubed of phi, right? And then cosine of theta happens just once. That's cosine of theta. Then sine of theta, that also happens just once. And then cosine of phi happens just once. All right? The rest of the things are just going to be the d phi, the d rho, d phi, and d theta. So at this point, we've transcribed the entire thing. I'm going to look at evaluating this integral in a slightly different way, more along the lines of what the Stewart textbook does. Because what we've been doing for multiple integrals is do the inner, then the middle, and then the outer. That's an okay way to do it. But in certain cases, like this, where the variables are not too mixed together, it's possible to actually separate them into 3 integrals that are then multiplied by each other. Here's what I mean. The original would be integrating along, let's do theta last, kind of do that usually, and then along phi, and rho would go from 2 to 4. Rho to the 5th, sine cubed phi, cosine phi, just keeping those together. I know that that's in a different order than how I wrote them before. And then cosine theta, sine theta. And this will be d rho, that was the innermost, and then d phi, and then d theta. What I can do here is actually pick out the parts that have the rho, the parts that have the phi, and the parts that have the theta, because they're not too intermixed. Like there's nothing here that says like sine of phi plus theta or anything like that. I can actually separate these out into 3 integrals that are all multiplied by each other. So this will be integral of rho to the 5th from, from 2 to 4, d rho. And then because the other things were constants, as far as this was concerned, now we can multiply by the integral along phi from 0 to pi over 3. That's sine cubed phi times cosine phi d phi. And because from the point of view of both rho and phi, theta is constant, now we can also multiply by the integral along theta from 0 to 2 pi of cosine theta sine theta d theta. So I can just call these integrals by number. I can call this integral number 1, integral number 2, and integral number 3. And that way I don't have to keep on writing the inner, the middle, and the outer. Like the integrand can get kind of unwieldy. It can get difficult to write. So instead, I'll just evaluate the integrals separately. Let's take integral number 1. Integral from 2 to 4 of rho to the 5th d rho. This is going to be rho to the 6th over 6, evaluated at 2 and 4. And gee, you mean you don't know what 4 to the 6th power is? Well, count them up. 4, 16, 64, 256. Can you do this one? 1,024. And then times 4 one more time, and it's 4,096. So this is 4,096 over 6 minus 2 to the 6th power is easier. That's 64. 64 over 6. And 96 minus 64 is 32. So this is 4,032 over 6. 4,032 is even, and it's divisible by 3. That means that 6 will go evenly into it. So let's see. 6 goes into 3,600 6 times, and now we need 432 more. So it will be 600 and something. 432 more is 70 for 420, and then 2 more for the 12. So this would be 672. All right, now integral number 2. Integral from 0 to pi over 3 of sine cubed phi times cosine phi d phi. You may be wondering whether we're going to be doing that trickery with like the powers of sine reduced to cosine or whatever. But the fact that we've got a cosine phi multiplied by this means that it's ripe for substitution. So we can say u equals sine of phi. That means that du will be cosine phi d phi. Sometimes we solve for d phi in this context, but I'm going to ask you to stay flexible and say that this du is something that you should be able to recognize over here. So the du is already present in the integral, okay? We'd get the same result if we solved and canceled, but I'm going to ask you to be flexible. You should know more than one way to approach these things. And then the bounds, u of 0, sine of 0 is 0, and sine of pi over 3 is, this is a messy number, root 3 over 2. This then is going to become integral from 0 to root 3 over 2 of u cubed du. That worked very nicely. So this will be u to the 4th over 4, evaluated at 0, and root 3 over 2. Now don't despair, because when you raise a square root to a 4th power, because those are even numbers, then the root is going to go away. We're going to end up having, like over here, root 3 over 2 to the 4th. First of all, let's square it, and then we'll square it again, because that's the same as raising to the 4th power. So this will be 3 over 4 squared, which is 9 over 16. Okay, so this will be 9 over 16, but the over 4 down here, that hasn't been taken into account yet. So we do need that. This is going to be 9 over 16 over 4. So 9 over 16 times 4, which is 64. And now that's complete. And then that's minus 0 because you're putting in u as 0 there. So we don't really need to write that. Okay, so we have the results. I'm going to circle them now so that I can keep track of them. This is the result of integral number 1. This is the result of integral number 2. And now we need integral number 3. And that's this one right here. That's from 0 to 2 pi of cosine theta sine theta d theta. I just like this blue so much. Let's keep on going with that. Integral number 3. Oh, that's the wrong blue. Silly. Integral from 0 to 2 pi of sine theta cosine theta d theta. Now, remember, we've seen this before. When you have sine theta cosine theta, yeah, you can do a u substitution, or you can do a, you can also do a multiple angle identity. We did multiple angle identity in a prior video, so I'm going to say we'll do the u substitution this time. Let's say u equals sine theta, and then du would be cosine theta d theta. Once again, this is already present in the integrand, so this right here is du, and that should be good enough. Now for the bounds, u of 0 is 0, and u of 2 pi. Well, this is weird because u of 2 pi is also 0. So, like, what does this even mean? Well, okay, think about what it does imply. It implies that this is going to be integral from 0 to 0. Yes, both the same. From 0 to 0 of u du. Now, so far, we've just faithfully copied everything that goes on here. But what is an integral over this interval? It's not even an interval. It has no length. Well, the interval here has 0 length. So think about like constructing a Riemann sum for this. The rectangles don't even have a chance to have any width. So an integral over a single point set is always actually equal to 0. So, I mean, what the heck? Doesn't this, like, it shouldn't do this, right? Well, think about sine theta cosine theta. What will be the period of that function? Sine theta cosine theta. And here I am going to invoke the double angle identity. It's 1/2 sine of 2 theta. So sine of 2 theta has a period of not 2 pi. It's been cut in half, a period of pi. So it's going to be sine begins at the origin. It's going to be a single period in the first pi, and then another period in the next pi. Well, hang on. If you take this area and then compare it with this area, those are the same. Likewise, if you take this area and compare it with this area, those are the same as well. So no matter which way you look at it, the value of this integral does have to be 0. This is the third integral here. And so although we did all this complicated work up above, it's going to end up having just a simple answer of 0. So the final answer, like if you skipped all the way to the end and said 0, you wouldn't get credit for this question. But it's going to be the 672 from before times 9/64, but then equal to times 0, which is going to make the whole thing equal to 0. And that's the value of the integral. It makes you wish that you had done that integral first, because then you would have been able to see that all the other work wasn't necessary. But it's a useful exercise nonetheless.